All right, good morning, everybody. It's been a very hectic day for me. I just flew in. I had no idea how big this place was. So I worked up quite a sweat getting here and setting everything up, but all is good. I do have a lot of content to cover, and I only have about an hour and 15 minutes to do it in, so I'm going to have to move fairly briskly in order to try to get it all done. First, let me introduce who I am. I'm Jeffrey Richter, the author of several .NET Framework and Win32 programming books. In fact, I show the covers of a bunch of those books at the bottom of the slide here. This is my C# book. This is my Visual Basic .NET book. These came out about 2 years ago, but I'm just now negotiating with Microsoft Press to revise this for Whidbey. This book came out just a couple months ago, this .NET Framework Standard Library Annotated Reference. It's really by Brad Abrams, and then there were about 5 people who contributed comments to it, and I was one of those people. And then there's a couple of my Win32 books on the right. All in all, it's about 11 books. I can't believe I've been doing this that long. And in fact, after this session, well, I'll tell you a little bit about what I'm doing today, in case anybody wants to follow me around. Today is, of course, this session right now. Then at 11:45 to 12:30, I'm in room 20D doing the Software Legends panel. I'll be on that panel. Then around 12:30, I'll be at the bookstore doing a book signing for the Addison Wesley book. That's the one in the middle here. Then from 1:30, I'll be doing a book signing also at the bookstore for my MS Press book, which are the ones on the left. And then I'm pretty much out of here. And tomorrow morning, I have some other stuff to do in this afternoon with some meetings. Then tomorrow morning, I fly to New Orleans for a family wedding. I think all that's being recorded for the DVDs, too, by the way. So, unfortunately, I'm not hanging around here very much today. But if you wanted to come chat to me about anything, and I probably can't hang around too much after this session either, but if you wanted to come chat with me, the best place to reach me would be at the book signings. And if you wanted to follow up, you can certainly email me at jeffreyr@wintellect.com. Please don't get crazy. Please don't send source code with help me find the bug kind of thing in it. But if you had just some questions on the sessions or something like that, I'm more than happy to have any of you contact me and answer that. Okay, so that's what I'm doing today. I'm also the co-founder of this company called Wintellect. We have a booth in the exhibit hall, by the way. We're a company dedicated to helping clients ship better software faster. We have several services that we offer, a consulting service, a debugging service. We do security reviews, and we do various training seminars as well. I've also been a consultant on Microsoft's .NET Framework team since October of 1999. I have an office in Building 42 at Microsoft, and I go to a lot of architecture meetings and design meetings, and so I know a lot of the reasons why things were done the way they were, and in fact, in many cases, I've had some input into things being the way they are as well. I was also on the Indigo team for 6 months, then I had a baby, so then I took a leave of absence there for a little bit, went back to the runtime team, and now I'm on the version architecture sub-team within the runtime at Microsoft, and we're trying to improve DLL hell. By improve it, I mean actually make DLL hell a worse thing, not a better thing. And the results of what we're working on won't ship in Whidbey, though. It'll be shipping in Orcus, but we have some really significant changes there to make Windows just seem more stable and make it easier for developers to version code and fix bugs and so on. Finally, I'm a contributing editor to MSDN Magazine, and I also write the .NET column there as well. All right, so without further ado, let's get into the talk at hand then. There are 3 main topics that I plan to cover in this session. The first is the Common Language Runtime's execution model. And in here we'll talk about intermediate language, and I'll give you some idea of what are the benefits of having intermediate language and some of the things it can do for you. Particularly, we'll talk about verification of the intermediate language, which is a procedure or function that the Common Language Runtime Engine does internally. It verifies the IL. And I'll mention some of the benefits that we as programmers and end users get from having this IL verification. I'll also talk about how JIT compilation works. JIT stands for just-in-time compilation. I'll go through that. We'll also discuss metadata. Metadata is kind of the technology that ties a lot of the parts of the runtime together, like the serialization engine, the garbage collector, the code access security system, the JIT compilation system, the execution model. All of these things are tied off of the metadata. And we'll talk a little bit about assembly loading as well. How does the runtime know when to load an assembly, where to go find that assembly and load it in, and so so on. And of course, the version architecture team that I'm on now at Microsoft, we spend most of our time focusing on that one area, and the changes will be coming down the line for Orcus. Our next big topic will be how things relate at runtime. So here, there's a lot of things that are happening inside the runtime engine. There is your code that needs to execute. Your code is for methods that are defined inside a type. So we'll talk about how does the runtime know what a type is? How does a type become a living, breathing thing inside the runtime engine? Then you can create instances of types, which are, of course, objects. So we'll show how instances of these types get allocated on the garbage collected heap. Then there's also, as your code runs, your thread is executing the code, and every thread has a stack. So we'll talk about the structure of that stack and what is being pushed and popped onto the stack at various times, and how you can have variables that you define inside your methods that are allocated on the stack, but they refer to instances of types that are on the heap. And then finally, we'll talk about the garbage collected heap, and I have a bunch of animated slides here to draw the relationship of all these things together and show you how the runtime uses this stuff at runtime in order to make your program function. And then finally, at the end, our next big topic is garbage collectors and how a garbage collector works. There are two different kinds of garbage collectors that are mainstream in the industry today. There's a reference counting garbage collector, and there's a reference tracking garbage collector. The garbage collector that we have in the .NET Framework Common Language Runtime is a reference tracking garbage collector, and I'm going to explain exactly how does a reference tracking garbage collector work, why a reference tracking collector was chosen over a reference counting garbage collector, and I'll point out some of the problems with a reference counting garbage collector. And then I have a couple of demos to walk you through as well to show you some performance and behavioral changes that occur with certain things when using our garbage collector. And that's the focus of this talk for the next hour and 15 minutes. So let's move directly into the execution model. As I'm sure you all know by now, you write your source code by basically placing it into a text file. In fact, I still know a lot of people at Microsoft who use Notepad as their editor of choice, mostly because it loads a lot faster than Visual Studio loads. Significantly faster. But you don't get IntelliSense support and color coding. But maybe somebody will work on a version of Notepad that does that for us. Anyway, you write, so that's what the boxes are, the rectangles or the squares at the top of the slide. You write your source code picking whatever programming language you want. You could write your source code using C# if you'd like. You can write your source code using Visual Basic, C++, Fortran. And basically, when you write your source code, you are describing the intent of what you want your program to do, and you're picking some programming language to express or describe the intent of how you want this code to run at runtime. And we use these high-level programming languages because it's just easier for us as programmers rather than working with some kind of assembly language or low-level kind of thing. Now, after you've picked your programming language of choice, you need to run that source code through the corresponding compiler, which is the rounded rectangles I show in the middle bar of the slide. So you would run your C# source code through the C# compiler, your VB source code through the VB compiler, and so on. The compiler, of course, opens up the text file and processes the syntax in it, and it expects the syntax to match that language of choice. To me, a compiler is really just a syntax checker, and it's a correct code analyzer. The compiler just analyzes the syntax to make sure that it makes sense in that language of choice, that it is able to understand your intent of your code that you are describing and produce IL assembly language as a result of that, this intermediate language, assembly language, as a result of that. In addition to syntax checkers and this conversion of your source code in the high-level language to this low-level intermediate language, the compilers also do correct code analysis for you. Like C#, for example, checks to see if you've defined an integer x, and then you want to read the value of x to display it to the console window. The C# compiler issues an error because x was never initialized. So it's just analyzing your code to see if it makes logical sense. That code could be converted into IL instructions, but the compiler is doing a little bit more than that to make sure that what you're attempting to do actually makes some logical sense. You're not trying to read a value out of a variable before the variable's been initialized. It's just one example of many that the compiler does. Now, the result of all these compilers is what we call a managed assembly, which are these I don't even know what color that is. Orange, pink, something. Besides, I'm colorblind. So these boxes at the bottom that are a darker color than these things at the top. The managed assemblies are exe or DLL files, and every managed assembly has 4 things inside it. 2 of those things are the most important, and that is the intermediate language bytecode itself, which we're going to take a look at momentarily, and then there's also the metadata. Now let's take a little bit closer look at what really is an assembly. An assembly is the managed equivalent of an exe or DLL. It's really an exe or DLL file as understood by Windows, because the Common Language Runtime is built on top of Windows, and Windows really doesn't even know anything about managed code. Now, over time, especially with Longhorn coming out, Windows and the Common Language Runtime will be stitched together more, and there will be some knowledge of the runtime built into Windows. But today, that's not the case. Having said that, there are about 2 things that actually were put into Windows XP that it knows about the runtime engine with create process and load library. Those 2 APIs were modified in Windows XP to know about the managed code, managed assemblies that we're producing here. A managed assembly implements and optionally exports a collection of data types inside it. Each of those data types can have some fields. Each of those data types can have some methods. Those methods, of course, have parameters, and so on. And an assembly is the unit of versioning, security, and deployment. When you create an assembly, you give that assembly a version number, like version 1.0. And all the types in that assembly are considered to be of version 1.0. It is not possible for you to say, here's a type in this assembly that's version 1.0, here's a type, and this type is version 2.0, and here's a type that's version 3.0. All types in assembly are given a single version number. They all share that version number. The same is true for security and deployment. We have this code access security system that's built into the runtime, and that sets up a fine-grained sandbox that the code is running in. And an administrator can say, I will allow all code in this assembly to have read and write access to the C drive. And it has to do it on an assembly basis. An administrator can't say, I want this type's methods, and this type is in the assembly, but just this type's methods to have read and write access to the C drive, but this other type's methods in the same assembly, I want it to have different permissions. The permissions are done at assembly granularity, not at the type, and certainly not at the method granularity. And then assembly is also the unit of deployment. Certainly, the only thing that we can copy onto a user's hard drive are files. You can't say, here's a file that's got 5 types in it, and I just want to grab these 3 and put them on the user's machine, and I want them live there. You have to copy the entire file. Now, as I said a moment ago, there are 4 things that are really inside an assembly. And here are the 4. There's the Windows PE header. PE stands for Portable Executable Header. And this has been defined by the Windows NT team about 15 years ago. It is otherwise known as the COF header information. All managed assemblies, exe and DLL files, need to have this Windows PE header at the beginning of them. Otherwise, Windows would not even be able to load the file into memory. So that was a requirement. As a side note, since this common language infrastructure has been standardized by ECMA, the ECMA standard says that all managed assemblies have to have this Windows PE header, even if they're running on the Apple Macintosh or on a Linux box or something like that. By the way, the first 2 letters of every executable are MZ, which stands for Mark Zibikowski, who was the guy at Microsoft many years ago who created the exe header, and now his letters, initials, are on every file, on every system in the world that's running the runtime. What a great position to be in. I envy that. I wish his initials were JR. That would have been better. All right, right after the Windows PE header is the CLR header. Windows operating system doesn't know anything about the CLR header at all. This is just I think it's around 72 bytes or something like that. It's not a very big header. But I'll show you in a moment a tool where you can see how big these headers are and what's actually in them if you care. The CLR header has information that is interpreted by the runtime engine itself and by various utilities that ship with the .NET Framework or the .NET Framework SDK or Visual Studio, or utilities that are created by other people like obfuscation tools and things like that. They would process this CLR header. Then, as I mentioned before, the 2 most important things that are inside an assembly are the metadata, which is type definition and reference tables. We'll take a closer look at those momentarily. And intermediate language, which is the conversion of your source code into this instruction set. normally we're familiar with compilers that convert your source code into x86 opcodes, while our managed compilers here, like C# and VB, they take your source code and rather than spitting out x86 opcodes, they spit out this intermediate language, and we get a lot of benefits from that. One benefit is it's much easier to write a compiler if you want to write your own compiler. But there's many other benefits that occur as well. There is a tool that is incredibly useful that ships with the .NET Framework SDK, and I would hope that all of you have some familiarity with it. I use this tool all the time, and it's called ILDASM, which stands for the Intermediate Language Disassembler. I'm going to run this tool for you momentarily, and this tool will allow you to look at the metadata that's inside a managed assembly. It's kind of like the dump-in utility that has shipped with Visual C for many, many years. Except this is a Windows GUI application rather than a console-based application. And this tool looks not just at the PE header information, but looks at the metadata and the intermediate language information that's in the assembly and displays it to us graphically. This is showing ILDASM letting you walk through the metadata. And again, I'll run this for you live in just a moment with a better example. Then we have intermediate language. All the compilers for the .NET platform have to spit out intermediate language. They take your source code and they spit out this IL. This intermediate language is a CPU-independent machine language. It was created by Microsoft, but Microsoft had input from many external commercial and academic language and compiler writers. In other words, they didn't produce it in a bubble. Microsoft had a lot of input and a lot of meetings from other people to really well-define this intermediate language instruction set. This IL instruction set, by the way, has had a lot of changes to it over the years, so it's still actively being worked on. For example, in WDB, we've had to modify a lot of the IL instructions to support the new generics feature that's in there. And this ECMA committee, one of the great things that's coming out of the ECMA standardization process is that the ECMA people get together and they have come from a myriad of different backgrounds and they care about different operating systems other than just Windows. And they care about other programming languages. Like Fujitsu sits on the ECMA committee and they worry about Fortran and COBOL. And they bring insight from these other languages into our system, and then Microsoft goes and adds additional IL instructions or maybe even modifies our compilers. If they see some other language has a cool feature, that might migrate its way into C# in some fashion. And that's probably been the best thing about the ECMA standardization process. In my opinion, it has been. Also, they review the documentation, so they improve the docs a lot, too. That's been another really good benefit of the ECMA standardization process. As a side note, I think Microsoft really wanted the ECMA standardization process to say that the .NET platform is all standardized, whereas Java is not, as a marketing thing. And in terms of that, I think that's been a waste of time. But I think that's what Microsoft was really shooting for. I think the real benefits were improvements in the documentation, and we have this bigger community that's built up that's bringing the platform forward in terms of new technology. This intermediate language is a higher level than most CPU machine language. For examples, in IL, there are no registers. You know, if you were writing x86 machine language, then you would be writing codes that put things in the EAX register, EBX register, and so on. You'd be doing all this register manipulation. Intermediate language has no registers at all. Everything is virtual stack-based. You have opcodes that push things on a virtual stack, and then opcodes that look at what's on the virtual stack, pops them off, performs some operation. Like if you want to add two numbers together, you might push a 5, push a 10, then do the add instruction, which takes the previous two things on the stack, pops them off, adds the result together, and pushes the return value, in this case 15, not a return value, but pushes the result, 15 onto the virtual stack, and then you might have some other opcode that says, now let me take the 15 and pass that as a parameter to some method or something like that. And we'll take a little bit of a look at that momentarily, so you get an idea of what IL looks like. There's not a lot of IL instructions. There's really very few. If you're compared to other CPU architectures, there's not a lot here, partially because everything is virtual stack-based. We don't have any registers at all. And in general, we have instructions to create and initialize objects, including arrays. So there's actually an IL instruction. As I said, IL is higher level than most assembly languages. Or machine languages. So we actually have instructions to create an object on the heap, call its constructor, and get the pointer to that object back. And that is one IL instruction called newObj. We also have IL instructions to allocate an array on the heap, initialize all the fields in it, and return back. That's one IL instruction to do that. We have IL instructions to call a method virtually. So the runtime can say, oh, I see there's this code that wants to call it virtually. Let me find out what type the object actually is and find the proper implementation. So it calls that implementation polymorphically, and it's only one IL instruction to do that. It would be several x86 instructions to accomplish the same task. There are IL instructions to throw and catch exceptions from code. And there are IL instructions to store values from the virtual stack into a field inside an object, or maybe load the value of a field onto the virtual stack. There's IL instructions to grab values and put them on the stack so you can call a method, so pass them as a parameter. And there's IL instructions to save things to and from local variables that you have inside your method. And after that list there of those 4 bullets, that's basically what IL is all about. I mean, there's, of course, methods to add numbers and subtract and multiply and divide and so on, too. But this is really the bulk of it. So it's very easy. And by the way, it's all fully documented, the IL instruction set. It would have to be so that people could build compilers for this platform because they need to spit out these instructions. It's also possible for developers to write in IL assembly language. You could do that. Open up Notepad or your text editor of choice, write the IL instructions, and Microsoft provides an ILASM.exe, which is an IL assembler. And since I work on the Common Language Runtime team at Microsoft as a consultant, in that team, I work around a lot of people who actually do write an IL assembly language every day. And it's probably really just on the north side of 2nd floor, Building 42. It's probably the only people in the world that actually do this, but I see it all the time. So I have no delusions about how often it's done. This shows an example of what some IL code looks like, and I'll walk you through it. This is for the equals method that's defined on the Boolean class, which is in the system namespace. And I'm using the ILDASM tool. In fact, why don't I run ILDASM here for you? Okay. I got to switch computers. Uh-oh. There we go. So I run ILDASM, and I would open up C:\Windows. Oh, this is not my machine. I hope everything is good. Oh, no, this is my machine. Everything is good. Microsoft.net. Let's pick this version. mscorelib.dll. mscorelib.dll is the most important DLL because it contains all the core types that are in the class library, like object, which is the base class of everything, the various integer types like int32, string is in here. So I'm always looking at mscorelib. If we go down here, so this tool is analyzing the metadata that's in that file mscorelib, and then I was going to find system.boolean. Where are you? System.boolean type here, and then I was going to look for the equals method, which is right here, and then we pop up the IL. So this is what it looks like. Here it's telling us that this is a method. It's a publicly exposed method, which is kind of interesting because it also means that you could find some methods that are not public. I don't know if Boolean has any. Boolean doesn't seem to have any. But I'm sure, how about in here? Well, internal block copy. This doesn't say public. It says assembly instead. This one's not a great example because there's no code here, but because this is a special method that calls out into unmanaged code. But we could look at privately implemented methods, and you could still see the intermediate language for the private methods. And a lot of people think that's a security issue because you're able to look at the code for private methods of a particular type. We don't consider that to be a security issue. We do consider it because the method can't be called at runtime. The runtime would forbid that because of verification, which I'll talk about momentarily. The runtime would forbid that. However, it is an IL, intellectual property protection issue instead, not a security issue, where you might have some IL code and then somebody could go and read that and reverse engineer what your algorithm does. But let's not get into that because that's a whole can of worms. So walking through some of this says that the method is virtual, so it would be called polymorphically. It's an instance method on the type versus a static method on the type. All instance methods have this hidden this parameter, which would be a pointer to the object, just like in unmanaged C++. The return value from the equals method is a Boolean, so it returns true or false. The method is called equals, and it takes one parameter of type object, and the name of the parameter is obj. That gives you an idea of how complete metadata is. Inside the metadata, it actually has the names of the parameters themselves, not just the type of the parameter. These are flags here that just says that the code for this method is common intermediate language, and it's managed code. Managed code means common intermediate language, really. Then inside here, this is a comment that says that the number of bytes for this method is 34. There are 34 bytes as the opcodes for the IL, and that's equivalent to 22 hex. Now, IL-DASM is this tool that's going to be used by human beings like you and me, and so it is converting the bytes into a human-readable equivalent here. These strings, if you will, are not what's actually stored in the file, because then the files would be enormous in size. So what's really being stored in the file are the IL bytecodes, the opcodes, which I'm going to show you a little bit later on. And this tool, IL-DASM, is reading those opcode values and converting them to this string in this edit control, really, so that I can make more sense out of it, rather than having to know that opcode 37 is a load arg1 instruction, for example. By the way, I don't know that opcode 37 is that. Proving my point for why it doesn't do it. This maxstack2, this is a directive, and it tells the runtime that this method, when it works with its virtual stack by pushing things on and popping things off the virtual stack, this method requires two, at most, ever, 2 slots on the virtual stack. In other words, it will never have more than 2 things placed on the virtual stack at one time. And this is just an optimization. It exists so that the runtime can produce slightly better code if it knows ahead of time what the maximum number is, because it needs to allocate some memory for that, and here we're setting it up. This method also happens to have a local variable that's defined in it. It's a Boolean type, and we don't have in the metadata the name for local variables. We do have in the metadata the name for parameters, but not for local variables. And so IL-DASM, the programmer who wrote this tool, IL-DASM, decides to just call this V0 for variable 0. Then we have the IL instructions themselves. So this says load argument 1, which is the pointer to some arbitrary object, because this is argument 1 here, onto the virtual stack. That's what that first instruction says. By the way, this here says IL offset 0. Notice this says IL offset 1. That means it's really 1 byte for the opcode for that load arg1.1 instruction. This says is instance system Boolean. So this says to the runtime, look what's on the stack, the thing that was most recently pushed on the stack, and check to see if that is an instance of the Boolean type. Because the equals method can only know how to compare a Boolean with another Boolean. So it's checking to see if what we're trying to see, if what is equal to a Boolean, if it's a string, then that should return false. This instruction ends up popping the value off of the stack and pushing a true or false on the stack, because that's the result of the is instance instruction. Is it an instance of Boolean will end up being a true or false on the virtual stack. This instruction says branch if true. So if the is-in said, yes, it's true, it is a Boolean type, then branch to instruction A, which would be down here. Well, if it's not true, that means that the object that we're comparing with a Boolean is not itself a Boolean. So we load a constant, which is a 4-byte integer, whose value is 0 on the virtual stack, and we return that 0 back from this method, so equals ends up returning false back to the caller. So if we try to compare a Boolean to see if it is equal to something that's of a string type, this ends up returning false, or 0, back to the caller. And now hopefully you understand how the IL is expressing that intention. Now in the case where it was a Boolean type, we branch to instruction A. Now we load argument 0 on the virtual stack. Well, this is an instance method. And all instance methods have this hidden this parameter that's passed into them, and that's always argument 0. So this instruction, load argument 0, is loading the pointer to some Boolean object that we're calling this instance method onto the virtual stack. Now we're going to take a field out of that Boolean object, and the name of the field is called m_value. And this was defined by some guy at Microsoft, that a Boolean type has a field in it called m_value, which coincidentally happens to be of type Boolean. This is a little confusing, but stick with it. So it takes the value of the Boolean, which is true or false, and it loads that onto the virtual stack. And it takes the value that was out of this object. That's the field out of this object and puts that on the stack. Then it loads argument 1, which is this guy, back on the virtual stack. It does this unbox operation, which I don't really want to get into what that is because it's a big can of worms there. So let's ignore it like it doesn't exist. And then this says load indirect that value. So here's where it's setting up to do the comparison. Well, it's loading the value from the other object also onto the virtual stack, and then we get to this guy here which says compare for equality to see if the two Boolean values, their fields inside, are both 0 or both 1. The CEQ looks at two things that are on the virtual stack, pops them off, and pushes on a true or false, a 1 or a 0. And then we get a return here, so this method ends up returning true or false back to the caller. All right, and gives you an idea of what's happening with the IL instruction set. Notice again there are no registers here. It's very easy to look at this code and understand what it does and to reverse engineer it. Now that being said, let me do one other example here. There are some really great tools out there. If you do want to reverse engineer somebody's intermediate language, the tool that I always use to do that is, let me get it here. Bin. Not mine, is Richter. This is a free tool. It was actually written by a Microsoft employee, but he's not on the Common Language Runtime team. And it's kind of amazing that he can make this available. Until somebody at HR, Human Resources at Microsoft, finds out, he'll be fired. But don't tell them. His name is Lutz Roeder. And if you go to Google and do a search for Lutz space Richter, this is an incredible tool. And it works very similar to IL-DASM. I can open up MS Corelib here, and I'm going to scroll down, and in the system namespace, I'm going to find the Boolean data type. Here it is, Boolean. And I open that up, and it has in here the same methods we were looking at before. Here's that equals method. And if I hit Control-D, it opens up this window here, for D for disassemble. And there's the same IL code. So it does the same thing that IL-DASM does, although if you hover over any of these, it pops up a tooltip giving you an explanation of what the instruction does, which is nice. Also, when you refer to anything, they're all hot, so you can click on it, and then it'll position you to another place here. But the real cool feature is that it also includes a decompiler. So it can take that IL code and convert it into C# code, which is much simpler to read. Okay. And of course, if that's too complicated for some of you, or you prefer to work in a different language, he supports Visual Basic, and he even supports Delphi. And he lets other people create add-ins that plug into this thing too, so you can get really any language that you want out of here. And how's that for intellectual property protection? But the great thing is, the comments don't come back. All right, so as you can see, I use this tool all the time, especially in some cases where the documentation sucks. The documentation has gotten a lot better over the years, but there are some places where the documentation is not quite up to snuff. This tool, I can look at a method and I can tell exactly what the method does. And this never lies. Sometimes the documentation lies. I can think of one API in particular where what it says in the documentation is exactly backwards of what the method actually does. I'm trying to think. I think it's the exact spelling field on the DLL import class. I think the documentation is exactly backwards. But with this tool, you can tell exactly what's going on, and then it never lies. All right, so I wanted to make you aware that these tools exist and kind of what IL looks like, and so on. So now let me go back to my slides. Oh, there we go. Okay. What are the benefits of having this intermediate language? Well, the big benefit that most people think of is that this intermediate language is not tied to any specific CPU architecture. So when I build an XE or a DLL with my C# or VB.NET compiler and it spits out this IL code, I could then take that EXE or DLL exactly as is, and I could run it on an x86 machine, which is what we normally do. But I could also put it on an Itanium box that's running a version of Windows that has a ECMA standard, or now it's an ISO standard version of the compliant version of the runtime engine, and that program would run there too. See, normally, with unmanaged code, you would have to recompile your source code into a different executable for each different CPU architecture. But in the managed world, that's not the case. You build it just once, you can deploy it to any system, any CPU architecture, even any operating system, as long as they have a runtime engine that adheres to the ISO standard, that code will run on that machine, including Windows CE boxes as well now. And many people believe that this ability to write your code once, compile it once, and have it run everywhere is the biggest benefit of having intermediate language. That's a great benefit for sure, but I disagree that it's the biggest benefit. The biggest benefit has to do with security and verification of the code. That's really the bigger benefit. Let's talk about that. When the runtime engine grabs the IL byte stream for a method, the CLR verifies that IL code to ensure that everything that code does is safe. This is a really cool thing, and it gives us as programmers a lot of confidence in our code. It also means that we have this execution engine that's now analyzing our code for any serious bugs. So the likelihood that we have bugs such as memory buffer overruns, or stack overflows, or stack underflows, which are also really commonly exploited in order to find security holes and give somebody administrator privileges on a box that they're not supposed to. The runtime engine is now actively looking for these kinds of bugs in the code because it can verify the IL and will ensure that these kinds of bugs don't occur, which also reduces the risk of security holes in the software that we write. It's really a big benefit, and over time, as Microsoft is itself moving more and more of its unmanaged code and rewriting it in the managed world, the number of security holes that we see in Windows will greatly diminish. And the same is true for any code that you write, of course. So some of the things that IL verification looks for. It looks that every method is called with the correct number of parameters. When you are calling a method in IL, there's a call instruction or a call vert instruction. You have to say to the IL, to the runtime, what method you want called. The runtime knows because of metadata how many parameters that method expects, and the runtime will verify the IL code to make sure you've pushed at least that many things on the stack prior to making the call. So the runtime has a way of ensuring that every method is called with the correct number of parameters. In addition, the metadata includes the data type of each of those parameters. And the runtime can verify that not only are you passing the correct number of parameters to the method, but that they are the correct data type. So it is not possible for you to call a method that wants a string and for you to pass in a pointer to a rectangle instead. The code, IL code, can be verified by the runtime, and it will ensure type safety and will ensure that whatever a method expects is what it's being passed. If the runtime sees something wrong with the IL code, it will throw an exception and will not allow that code to execute. I'm going to demonstrate that for you in just a moment. Another example of something that the runtime checks is that every method's return value is used properly. Let's say you call a method that returns a string, and you're trying to put it into a variable that's of type date time. The runtime says, hell no, you can't do that. And it can look at the IL code to see you're trying to put a method that returns a string into a local variable of type datetime, and it'll say, I don't know what this code's trying to do. It doesn't make any sense to me. The runtime will refuse to compile that code and will throw an exception, and if it's not caught, which is the usual case, then the application is terminated. But this potential bug, cannot be exploited. Every method has a return statement. If you wrote, let's say, an x86 assembly language, which generally nobody does anymore, but let's say that you were writing a method in x86 assembly language. So you write opcode, 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 and at the bottom you should have a return statement. But let's say you forget the return statement. Now you assemble your x86 code into an XE or DLL, and when this method gets called, the thread runs the code, and when it gets to the bottom, it just runs and executes whatever bytes there happen to be right after it inside memory. Well, the runtime can't allow that either. That's a potential security hole. The runtime verifies that every method that is written in IL has a return instruction at the bottom of it, or again, it will forbid to compile that code and will throw an exception and not let it run. These are just 3 examples. There are many examples of things that the IL verification looks for to make sure that your code is doing the proper stuff. And this metadata includes all of the type and method information that's used for verification. Inside this metadata is the name of the method. Also in there is the number of parameters. Also in there is the types of those parameters. Also in there is the type of the return value, unless it's void, of course. And the runtime looks at the IL instructions and the metadata to figure out that everything is working right. That, of course, comes at a perf hit because it happens at runtime, and we're going to talk about that more very shortly, in about a slide or two. So what are the benefits of having this safety check on the code? Well, we have a bunch of benefits. One is all this type safety and security holes that get filled up so that they're much less likely to happen. Another is the following. If you think back to when Windows NT was first being created 15 years ago, one of the big features of that operating system was that, compared to 16-bit Windows and DOS, Windows NT ran every application in its very own address space. And the great thing about that was that the code running in here had no way to read or write to any data that was owned by another process. So if this program had a bad pointer and started doing some crazy stuff in there, it would have no bad impact on any other application that was running on the machine. But now if you think, what is the requirement on Windows in order to offer that support? Well, you have to create a brand new process. Creating a process in Windows is probably the most expensive operation you can do. In fact, the create process Win32 API is probably the slowest API of every Win32 API you can think of. And the reason is because Windows has to create a process kernel object, has to create a thread kernel object because there'll be a thread in that process. It has to initialize those kernel objects. It's got to create a bunch of virtual address descriptors to virtualize a 4 gigabyte virtual address space for the process. The thread has to have a stack that's 1 megabyte in size for the user mode stack, but there's also a kernel mode stack for the thread. Then it has the runtime, or the Windows, has to go and load the executable into memory, find all the DLLs that it requires, load those into memory, and so on. It's an incredibly expensive operation to create a process in Windows. When we move to 64-bit Windows, then we have to virtualize a 16 exabyte address space, which is significantly bigger now than a 4 gigabyte address space. And this ends up using a lot of operating system resources, like internal memory, to manage a process, and of course all the CPU time required just to get the process up and running to begin with is pretty bad. Now enter managed code. With managed code and the runtime's ability to verify the IL to make sure that everything that the code does is safe, it's actually conceivable that we could run all managed applications in a single address space. Not only is it conceivable, but we actually do it. If you build an ASP.NET web form application or an ASP.NET web service application today, ASP.NET has this worker process, and inside the worker process, let's say your website is hosting 100, your web server is hosting 100 different websites. We load the code for those 100 different websites that could be created by different companies, because let's say you're an internet service provider, and we'll run them all in one process. And there's no fear, if all that code is written in C# or VB or a managed language, there's no fear that one of those websites could have some code in it that might try to steal passwords that are being used by another website, because the runtime has this IL verification step to ensure that everything is used the way it was intended to be used and no violations can occur. This means that we're creating far fewer processes in Windows, which means much less operating system overhead to manage the applications that are running. That frees up a lot of memory, which now goes to your applications, so your applications have more memory, and the system just runs better overall. You have a question? I didn't say I was taking questions, but all right, fine, I'll take a question. Go ahead. What's your... Yeah, his question is, if let's say your managed code called out into unmanaged code, then aren't all bets are off at that point? And the answer is yes, then all bets are off. But that is why the runtime requires that you have a security permission for managed code to call out into unmanaged code. And if the administrator sets up the managed assembly, remember because security is done on a per assembly basis, to say code in this assembly is not allowed to call out into unmanaged code, which is the default, then if it attempts to, that would throw an exception which could be caught and we could terminate that website, but the process would stay up hosting all the other websites just fine. Okay? So we have a security privilege in order to get out into unmanaged code, which by default would not be granted in that case. Administrators can now trust all these applications to run. And I heard, and it's so far out that who knows for sure, but I heard that in Longhorn, there will actually be a way for you to create like a Windows form app and mark it with some settings to say when the user clicks on this in the shell or runs it, that this application doesn't need its own process. It can run in a shared process. And we would encourage more people to build applications that can run in a shared process to reduce the operating system overhead and allow more applications to run on the machine with fewer resources. All right, so I already mentioned this thing about ISPs. I'm sure you've heard this week that one of the new features in WDBI is the ability to load the runtime engine inside Yukon, the next version of SQL Server. And when this managed code is running inside the database, I mean, Microsoft gets the heebie-jeebies when they think about people putting code inside the database. Who knows what that code is going to do? It might bring down the database and so on. But now, because we have this IL verification, we feel very comfortable putting managed code inside the database because the runtime verifies that everything it does is safe. And again, we can prevent it from calling out into unmanaged code. Any code that comes in over the internet, like somebody sends you a link or you get an email message with a link to click on, and that might download an executable onto your machine. As we know today, a lot of times that's a very scary thing to do because who knows what these executables do internally. Probably right inside main, they spawn out the command.exe and do a format C: for you. So with managed code and the verifiability and with code access security, all of that can be prevented, and it can make the computers a safe place to run code that comes into you from anybody. And since you've locked down your machine, we'll just run that code, and it might throw an exception and fail, and we would want that if it tried to do something we don't allow it to do. And it is possible for an administrator to turn off this verification, but obviously that's strongly discouraged. Thing to do, in which case the code just runs just like an unmanaged C or C++ app would today. So however well you trusted that, if the administrator turns off verification, they're basically making the same statement. I trust this managed code to be just as good as unmanaged code, but then all bets are off. So we discourage administrators from doing that, but they can. All right, now we'll talk about the execution model. I'll explain all these steps as we go through this graphic over here. Oh, I am way behind schedule. All right, so I'm going to talk really fast now, like I wasn't doing that before. Main starts running. The thread's going to call console write line. At that point, the engine has to go out and find the assembly that defines the console class. That's mscorelib.dll. The runtime goes and loads mscorelib. In reality, it would already be loaded because that has object to base class of everything. Then the runtime needs to create this green rectangle here. That's the internal data structure that is used by the system that means the console class is alive and well. Inside this object, this data structure, there's this method table, we call it. It is an array of function pointers. There's be one entry in here for every method that's defined by the console class. C++ has a similar thing. In the unmanaged world, it's a virtual method table. Our method table is for all methods, statics, virtuals, non-virtuals. It has an entry in it for every method, whether it's virtual or not. All of these pointers would be initialized to point to this function called JIT compiler, which is in MS-Core EE, which is the execution engine itself for the runtime. Now, when the thread wants to call console write line hello over here, the runtime has to find the console class in memory, look up the write line method that takes a string, so that's the second entry over here, and see what this points to. Because when this block was initialized, this is initialized to point to the JIT compiler function here, the runtime now jumps into this function. What this function does internally is the following. In the assembly that implements the new type, so the type is console, the assembly is mscorelib.dll, look up the method, in this case the write line method, and in particular the write line method that takes a string. We would look that up in the metadata. From the metadata, we would grab the IL for the method and verify it. The runtime would do that. Let's assume it verifies successfully. At that point, the runtime here allocates a block of memory inside the unmanaged heap. This is all in unmanaged code. In fact, they literally call heap alloc the Win32 function, in order to allocate this block of memory. And then the JIT compiler converts the IL code into native CPU instructions and places those x86 or Itanium or Opteron opcodes inside this block of memory here. So it has basically compiled at runtime the IL, and it's very fast to compile IL code into x86 code, because IL is already this intermediate representation that just naturally can be converted into x86 instructions or Itanium instructions or Opteron instructions, which is x64 instructions. After this is done, then this method here modifies this pointer so that instead of pointing to JIT compiler, it now points to this block of memory that was allocated. And then finally, this method jumps to the native code. So it jumps over here. The x86 instructions are now running, so it's now executing what the write line method that takes a string would do. And then when it returns from here, there's a return instruction in here. We return back over here into main. Now when we call console write line goodbye, again, the runtime goes to the console class, looks up the write line method, but now this doesn't say JIT compiler anymore, it says native method. At that point, the runtime jumps right over here to the x86 code, and now it's running at full speed. The verification process only happened once. All right? And every future call to this console write line method is running at full speed now. Just as fast, if not faster, than if you had compiled it with an unmanaged C or C++ compiler. And then, of course, when this returns, we go back into main. Main returns back. And in the second call, none of the stuff at the bottom had to happen in the slide. Okay, so that's the execution model. Now, a lot of people ask me, is this information saved anywhere? I don't want to spend a lot of time on that, but the answer to that is no. When the process shuts down, all these x86 instructions are completely thrown away, and the next time you run the application, it has to start all over again. We could spend the next 15 minutes easily talking about things related to that, but we're not going to. So let's move on instead. We're going to talk about metadata. This is your canonical Hello World application, although it's a slightly simplified version. It's just your hi. If you were the compiler, here's how you would process this. You would look at the first line of the code. Now, I wrote it in C#, but it would be similar for other compilers. The C# compiler says, oh, I see what the programmer is trying to do here. The programmer is trying to define a class called app. And what the compiler will do during compilation is it will create a block of memory. And that block of memory contains what we call a type definition table. And the compiler will add one row to that table that says that this source code is defining a type. That's why it goes in the type definition table. And the name of the type is called app. And there would be some flags in that entry in the table, too, like it's a public class. It would also indicate in the table what the base class of app is. Now, I don't have it here explicitly, but implicitly, all types are ultimately derived from system.object. So that would also be written out into that row in the type definition table. Then the compiler gets to the next line of code, public static void main. Here the compiler sees that the programmer is trying to define a method called main. And the compiler will create in memory a method definition table. And it will write one row into that table that says there's a method called main. Furthermore, it will add to that row some bit flags indicating it's a public method and it's a static method, and that main has a return type of void and takes no arguments. Then the compiler gets to the third line of code, which is a very intense line of code. The compiler sees that the programmer is defining a string called hi. So there's a string definition table, which will get the literal string hi placed into it. Then the compiler will see that our program is referencing, not defining, but referencing the system.console class. So there will be a type reference table that gets one entry in it for system.console. The compiler will see that we are also referencing the write line method that takes a string. The compiler will create a member reference table and put one entry in it for write line. The compiler will also figure out that system.console, that type is defined in mscorelib.dll, and the compiler will create an assembly reference table and put one entry in it saying that this program needs to reference mscorelib.dll in order to run. Notice how much talking I've been doing, and I've not even talked about compiling the code. The compiler has spent most of its time producing metadata information about all of this. Now, finally, the compiler also has to convert that code into IL, and that ends up being 3 IL instructions. Load hi on the stack, call, write line, return are the 3 IL instructions that end up getting produced from that. All right, this is a list of some of the metadata tables that exist. I'm not going to go into it in a lot of detail. I already mentioned there's a type definition table. It's got one entry for every type that's defined in your source code. Each row includes the name of the type, what it is derived from, some bit flags, whether the type is public, private, and so on. And it has an index into the method definition and field definition tables, if that type defines any methods or defines any fields. There's a method definition table. It's got one entry for every method you've defined in your source code. Each entry includes the name of the method, like main, some flags, the offset to the IL code for that method, and indexes into a parameter definition table, which has one entry for every parameter of that method. Also return value. And then there's a field definition table, and I think you get the idea. By the way, there's 47 metadata tables that are defined today. That number is growing because we had to add some new ones in order to support generics and would be. So we're free to adding more if we want to. But all that gets standardized. There's also reference metadata tables. And again, here's a partial list of 3. There's an assembly reference table that's got one entry for every assembly that you refer to, like the name, like MS Core Lib, a version number, culture, and a public key token. A type reference table that has one entry for each type that you're referring to, like system.console, and an index into the assembly reference table for which assembly implements system console. So system.console would be in MS Core Lib. And then there's a member reference table that's got one entry for each member referenced by your source code. And each entry includes the name, like WriteLine, the signature, it takes a string and returns void, and has an index into the type reference. So WriteLine is in system.console, which is in mscorelib.dll. All right, so this is all being built up by the compiler at compile time. Then when the compiler spits out the resulting exe or DLL file, all of this information is put into that file itself, in the resulting exe or DLL, and then this tool like ILDASM or Lutz's Reflector application, they can load in those files, and they can show you that metadata, and I've already demonstrated that for you. All right, and since I did that demo, I'm just going to move on for time. Okay, man, I am really out of time. Well, these are the actual byte codes. Very quickly, every piece of metadata has a number to uniquely identify it. That number is called a metadata token. It's a 4-byte number. And these are what those numbers look like. You can see them with ILDASM. This first byte of a metadata token, in this case 06, means table number 6. Table number 6 is the method definition table. And then the last 3 bytes is the index or the row in that table. That's what a metadata token is. So now to put it all together, in IL, you could have a call instruction that says something like, I want to call, well, this number isn't quite right. It's not showing me the number I want in this slide. But this would say, the thing I want to call is in table number 1, entry number 3. And let's say the table number 1 was the method reference table. So it would go and find, that's WriteLine. From that table, it would find out what type defines it. From that, it would find out what assembly defines that type. Then the runtime would load that assembly into memory, go to that assembly's type definition table to create that console green rectangle I showed you before and initialize the method table inside of it. Then it could find the WriteLine method inside there and then make the call to it. And that's how the whole type system comes together and how these things end up, types come into the system and start running. So in the IL stream, what I'm trying to show with this slide is in the IL stream, there's 1 byte opcode for call, and then there's a metadata token after that. The metadata token indicates which metadata table and what row in that table is the thing we want to call. From that, the runtime is able to extrapolate all the other information in order to load the proper assembly and call the correct method. All right, and then this slide here shows kind of a flow chart. You can have IL with a metadata token. That metadata token could be something in the method definition table, which means you're calling something in the same assembly. So we can go to the method definition table, find out what type it is, and create the internal structure for that type, and then we can allow the call to occur. If the IL call instruction is a member reference, we go from the member reference, we can find out the type. From the type, we can find out what assembly. Then the runtime can load the assembly into memory, look up that type in this assembly's type definition table to create the internal data structure for the type, and then we can go and make a call to that method. I know I'm moving very quickly. All right, that brings us to our next topic, and we're already over time. That's going to be a problem. Would you rather hear this or how a reference tracking garbage collector works? How many people this? Okay, how many people garbage collector? This, I think, is the winner. So we're going to stick with this. All right, very quickly here, because in this slide I don't really show anything new. The big box is a single Windows process. Inside it, the runtime engine has loaded. The runtime has a thread pool and it has a managed heap. There can be many threads that are running in this process. Each thread is given its own stack. That's what I show here as one of those thread stack. That thread has been executing some code for a while, so it's been using its stack, and that's the green area at the top. Thread stacks always build from high memory addresses down to low memory addresses, by the way. Now we introduce a method. Here's this method M1. Inside the method M1, we have a local variable that's defined called name, which is of type string. The memory for local variables is allocated on the thread stack. So there will be memory on the thread stack allocated for this thing. This is actually a 32-bit pointer. If you're on a 32-bit system, it'll be a 64-bit pointer if you're on a 64-bit system. Now on the next line of code, so this pointer would point to this string Joe, which would be in the heap. Here, I want to call this method M2, and I want to pass in name. In order to call a method, we have to push the parameter. Here's M2, by the way. We have to push the parameter on the stack and then call into this method. Whenever you call to some other method, the CPU itself puts the return address of where to return back to on the stack. So the return address will be pushed on. Now our thread is executing the method M2. M2 has some local variables, and the memory for those will be allocated on the thread stack. This is all the way it works in the unmanaged world too, by the way. There's nothing here that's .NET specific, but then I'm going to get into a .NET specific twist momentarily. M2 continues running. It does whatever it needs to do. Ultimately, when it gets to the return statement here, we're going to return to this address, which unwinds the stack. Now we're executing back here in M1. We get to a return statement in M1, which again unwinds the stack. So now the stack looks just like it did before M1 was called. We've cleaned everything up, and as I said, there's really nothing new here. This is the way it's been working for many, many, many years. Now we'll put a .NET twist on it. Here we have a class called employee, which is implicitly derived from object. I've defined three methods in here. One's an instance method called getYearsEmployed. One is a virtual instance method called generateProgressReport. And one is a static method called lookup. Then I've also created a class called manager that's derived from employee, and it overrides the virtual generateProgressReport method. So I have the methods. These are all the different kinds of methods that you can have inside a class, and the virtual one I'm overriding in the derived class. Okay. Now, of course, when you write that code, it's kind of as though this mapping is occurring internally. All instance methods are effectively becoming like static methods, and they get as their first parameter this parameter, this hidden this parameter, that's of the same data type of the class that the method is defined inside. This is also the way it worked in unmanaged C++ for many years. So there's really nothing new here either. Okay? So these two instance methods, one was virtual, one wasn't, they kind of become like static, and they now get a parameter where they didn't have that before. A static method just stays, and its signature doesn't really change at all. And it doesn't have a hidden this parameter because it's static. That method's associated with the type itself, not an instance of the type. And then when you write code to, let's say, new up an employee and call, you write syntax like this in C#. So here's a variable I'm calling these instance methods. The C# compiler is effectively calling like these methods that look static now and passing the pointer in. But that's really happening underneath the covers in the runtime. And again, that's also the way it works in unmanaged C++ today as well. And it is this hidden this parameter is what makes instance data available to the instance methods, just like in the unmanaged world. In the IL instruction set, there are two methods that are available to call a method. There's a call method, which you can use to call a static method, instance methods, or a virtual method. So there's a call IL instruction. And this method does no null check on the this pointer. So when you say I want to call an instance method, if the variable that you're using contains null in it, it doesn't care, and it just calls that instance method on that type. Now the this parameter that gets passed in will have a value of null. But it calls the method, and now the method gets to run, but the this parameter will have a value of null. And the compilers use this also if you have a virtual method, but you want to call your base class. Like let's say you override the onPaint method of a button class or something, and then you want to call base onPaint. We don't want to call that virtually because we would end up with an infinite loop. We'd get infinite recursion. So the C# compiler will emit a call to the call instruction here in order to call the base class because we don't want that method called virtually in this case. Now, we also have a callVirt IL instruction, which is usable for instance and virtual methods only, not for static methods. You cannot call a static method using the callVirt instruction. You'll get slower perf with callVirt because it has to figure out the pointer. Here's a pointer to an object. What type of object is it? So it knows which data structure to go into the runtime to find the proper method so that it can call the proper implementation of that method. That's what it means to call something polymorphically or virtually. The callVirt method, or IL instruction, always does a null check when you call an instance method. So if I try to call an instance method with callVirt, and the pointer to the object I'm passing contains null, the runtime will check that, and it will throw a null reference exception and not allow the call to even occur. And C# and the VB compiler guys, it's kind of surprising, they chose to use the callVirt IL instruction even when calling a non-virtual instance method because they always wanted that null check done. And you can see that here. This was a choice of these compilers. And it slows down perf a little bit, but they thought they would get some benefit in helping programmers a little bit. So they chose to value helping programmers write better code over better perf. In this code here, for example, I new up an object and I call getHashCode. GetHashCode is a virtual method on object. And here we see the IL instructions for that call. The C# compiler emitted the callVirt IL instruction here, which you would expect because it's calling a virtual method. But here we see I'm calling the method getType. GetType is a non-virtual instance method, but if we look at what the C# compiler produced, it put a call to callVirt here, which seems very odd. Why call this method virtually when it is not a virtual method? And the reason why they did that was because they wanted to benefit the null check that callVirt does. So if E happened to be, or O in this case, happened to be null, I would get a null reference exception at the call site rather than a null reference exception inside the getType method. And this was a language choice. And here I'm calling a static method of a class. You cannot use callVirt for that. And so the C# compiler uses the call IL instruction in order to do that. All right, so now let's tie all this together, and then we're going to bring this to a close. And I'm sorry I ran out of time. This is that thread stack we were talking about before, and it took me 3 hours to get PowerPoint to slide that over here and shrink it down. So I'm very proud of that. I always make mention of that whenever I can. 3 hours wasted time. Now let me introduce to you the managed heap, which we had not talked about before. Everybody, managed heap, this is everybody here. And now let me introduce a method. Now notice a bunch of things just popped up. When our thread called into the method M3, the compiler had to grab the intermediate language for M3, verify it to be sure that everything it did was safe. Then the compiler also looked and see what types are being referenced in M3. And it saw the employee was being referenced, int32 was referenced. There's a string being referenced over here, and there should be a manager. Yeah, manager is also being referenced. Now let's assume that string and int32, since they're such common types, we use them all the time, that they were referenced earlier in the program. So let's not worry about those. Instead, let's pretend that when the thread calls M3, it's the very first time that manager and employee have ever been used by this program. Before, there may be code in there, but the code was never attempted to be executed that used those types. At the time when the runtime verifies the IL for M3, the runtime has to make sure that these types, employee and manager, are actually living, breathing things. At that point, the runtime finds out what assembly defines these types, using what I described to you earlier, loads that assembly into memory, looks at that assembly's type definition table in the metadata to find the manager type and the employee type, and then it creates a manager type object and an employee type object inside the manage heap. These are type objects. There's one for every type that is currently in use in your program, and as your program continues to run and uses, maybe calls new methods that are using new types you haven't used before, the runtime has to go and make these types living, breathing things, but all this is done just in time, if you will. We lazily get all this information. We do not eagerly get it because it would slow down initialization time of your application too significantly to do that. Every type in the heap, or every object in the heap, has two overhead fields, a method table pointer and a sync block index. Also, when you define a type, that type might have some static fields that you define. Memory for those static fields has to come from somewhere. And the memory for those static fields is allocated in the type objects themselves. Now, in my case, when I showed you my code for the manager class a few slides back, I didn't define any static fields. But if I had defined some static fields, the memory for them would be allocated inside this manager type object. Similarly, if I had any static fields defined in my employee type, memory for those would be allocated here as well. And then what I show at the bottom here is the method table. That we talked about before for console write line. The console class had all the write line methods in it. There would be one entry in here for each method defined by that particular type. My employee type defined three methods: get years employed, generate progress report, and lookup. And so there are three entries in this table. Manager type overrode just one of those methods, generate progress report, and so there's just one entry in here for that method. That was the setup. Okay, now the thread calls into M3. It has two local variables, and the memory for local variables goes on the thread stack. Also, the runtime ensures whenever you allocate a local variable on the stack, the runtime ensures that the value of that variable is always zeroed out. You know, in the unmanaged world in C and C++, if you had a function and you had some local variables, they would be initialized to whatever garbage was on the stack. That opened up security holes, robustness issues, and so on. So the runtime takes the perf hit of zeroing out all local variables when they're created on the stack so that your program runs predictably all the time and there's no potential security hit. In addition, by the way, whenever a new object is allocated on the heap, the runtime also always guarantees that all the fields in that object are zeroed out as well. Again, for robustness reasons and security reasons, it always does that, and we're willing to take the perf hit in order to get robustness, better robustness and security. On this next line of code, I'm newing up a manager object. So that creates this manager object in the heap. Every object on the heap has a method table pointer and sync block index. Those are 32-bit values each on a 32-bit system, 64-bit values each on a 64-bit system. The method table pointer is really a bad name. It actually points to the type that the object actually is. The sync block index has something to do with thread synchronization. We're not going to get into that. Any instance fields for the type are memory for the instance fields is allocated in the type object here itself. So if I had defined any instance fields on the manager class, memory for them would be allocated in this object. Then the new operator returns a pointer to this object on the heap, which I place in the variable e, which is on my thread stack. So e points to this object. From the method table pointer, we can see what type that object is, or the runtime can make that determination. Now, in the next line of code, I'm going to call the static method lookup on the employee class. In order to make this call, the runtime has to go to the employee type object, because it's a static method, find the lookup method here, call it, passing in the string Joe. That's going to cause that method here to get JIT compiled now. And then it runs. Now, let's say internally that method looks up Joe inside a database and figures out if Joe is a manager or an employee. Then the lookup function news up an instance of the manager or an employee class, and in this case, it newed up a manager. So Joe was a manager. The pointer to that object is returned back, and I place it in the variable e. So e now points to this manager object on the heap, whose method table points to the manager type, because that's what type this is. You'll notice that this manager object over here is orphaned. There's no field or variable in my code that refers to it anymore. It is orphaned. It is a prime candidate for garbage collection sometime in the future. Now, the next line, I'm going to call getYearsEmployed. GetYearsEmployed was a non-virtual instance method, which means it is called using the static type of this variable here. In other words, the compiler knows that E is of type employee at compile time, and so we need to go to the employee type, look up getYearsEmployed, and that's how we know to JIT compile the code here. Let's say it runs, returns a 5 back, which I place in the variable year, and here you see I've changed year to point to 5, right, or has the value of 5. And then finally, I'm going to call generateProgressReport, but this is a virtual instance method, which means it's going to be called using the dynamic type of E. Well, because the callvert instruction is used here, and because the compiler and runtime know that this is a virtual method. So in this case, what has to happen is we have to take E, we have to follow it to the object it is. From the object, we need to follow the method table to find out what type it is. Then we can look up generateProgressReport here, and that's how a method ends up getting called virtually or polymorphically in the runtime. Okay? Well, and there you have it, I think. And in this code, the way it was written, the code for the employee's generateProgressReport never got JIT compiled. So that's to show that in this code, the way it was, that never got JIT compiled. Now, as a side note, if the lookup method discovered that Joe was an employee instead of a manager, then when we executed this line, then this would have gotten JIT compiled, and this would not have gotten JIT compiled. Okay. All right, I think that's going to bring us to the close. I ran 15 minutes over. In fact, I'm supposed to be in the other room right now. Yeah, all right. So sorry I ran out of time. Thank you. Again, feel free to look me up at the bookstore. If you want to talk about anything, you don't have to buy a book to have me sign it. Also, feel free to email me. Again, it's jeffreyr@wintellect.com.